So far in section 1.3, we learned about a new number called the imaginary unit, which we represent with the letter I. I is defined to be the square root of -1, and as a consequence, I squared is equal to -1. And we saw some examples of pure imaginary numbers in the previous video. They were the answers to some of the problems that we worked. So for example, 3i or I root 10 or the others you see there on the screen. And so now we want to come to the definition of a complex number. So a complex number is any number of the form a plus bi, where I is the imaginary unit and a and b are real numbers, numbers that we were familiar with before we got into the imaginary unit. So let's have a few examples. So 4 plus 5i is a good example of a complex number. A complex number has a real part and it has an imaginary part. And so those would be the two terms in the complex number. It might be worthwhile just to step back and think about what we're saying about 4 plus 5i. 4 plus 5i is a number. It's a special kind of number called a complex number. If you looked at it before today, you would think of it as two separate numbers. And indeed, there are two separate parts, a real part and an imaginary part, but we can take the whole thing together and think of it as a single quantity, as a single number, a special number called a complex number. Okay, so 4 plus 5i is a fine example of a complex number. You could just as well use square roots, like the square root of 3. You could just as well use a fraction. The numbers could be positive or negative. Sometimes when I'm teaching this class face-to-face, I ask, okay, what is the value of a in this complex number? And so you would say root 3. And what's the value of b? The value of b is -1/2. Yeah. And then let's have a couple more examples. What about 3i? Is 3i a complex number? A lot of times students say no, because it's missing the a in front, right? It's got the imaginary part, but not the real part. Well, actually, yes, it is a complex number. And if you think about it, right, what is the real part? And the value of a would be this number 0, because 3i can be written as 0 plus 3i, then 3i is a complex number. Complex numbers where the real part is 0 are called pure imaginary numbers, and so we have a few listed out here up above. Okay, and so then let's have another example. What about the number 4? Is the number 4 a complex number? Usually by this time a student catches on and says yes, it's also a complex number. And they see that since the imaginary part is missing this time, that just means that the value of b is 0. So 4 can just as well be written as 4 plus 0i, and then it has all the parts that it needs in order to be called a complex number. It has the real part 4, it has the imaginary part 0i, it has a value of a is 4, and a value of b is 0. Numbers like this, where the value of b is 0, are called real numbers, are called real numbers. What does this mean? This means that any real number is a complex number whose value b is 0. Okay, we'll talk about that a little bit more later on in the section. For now, what I want to do is I want to take complex numbers and I want to add, subtract, multiply, and divide them. And so let's go ahead and call this, I think we're up to example 3. I think we had 2 examples in the previous video, and so this would be example 3. And we'll say add, subtract, multiply, and divide. And so the first example will be 3 plus 2i plus 9 minus, I don't know, how about 7i. Okay, so we're adding 2 complex numbers. The first complex number is 3 plus 2i. The second complex number is 9 minus 7i. You might be able to guess how we're going to do this. We're going to combine the real parts. 3 plus 9 is 12. And then we're going to combine the imaginary parts. The plus 2i minus 7i gives us minus 5i. 2 minus 7 is negative 5. And then our answer is 12 minus 5i. So really all we did was combine like terms. 3 plus 9 makes 12. 2i minus 7i makes minus 5i. Okay, so then let's go ahead and subtract. Let's do 3 plus 2i minus 9 minus 7i. And so here, what we might like to do is just go ahead and drop the parentheses. I don't know if you thought about it or not. In the first example there, in example A, we didn't really need the parentheses in order to get to the answer. The parentheses just help us to see the problem as the sum of 2 complex numbers. Here it's the same thing. We have the difference of 2 complex numbers, or we have a subtraction problem. Of course, now the parentheses make a difference. When we subtract what's in the parentheses, then we need to distribute that minus sign to each term inside the parentheses. And so the first step might be just to write 3 plus 2i and then distribute the negative and say minus 9, and then minus a negative is plus 7i. And then of course combine like terms. 3 minus 9 is negative 6, and plus 2i plus 7i is plus 9i. So negative 6 plus 9i. Okay, so the addition and subtraction aren't too tricky. I think the multiplication is okay too. It's the division where it gets a little bit harder. So let's go ahead and try a couple multiplication problems, and then we'll do the division after that. So let's go ahead and do 3 plus 2i multiplied by 9 minus 7i. You've done a problem very similar to this, except instead of i's, you had x's. And so actually we can treat the I just like we would treat the X. We can distribute the 3 plus 2i to each term in the next factor. Or we could, some of you learned this as FOIL. FOIL stands for first, outer, inner, and last. And I'll try to write that out here. Let's write the 2 first terms. 3 times 9 is 27. The 2 outer terms. 3 times negative 7i is negative 21i. To inner terms next, 2i times 9 is positive 18i. And then the two last terms, the 2i times negative 7i. Be careful here. 2 times negative 7 gives you negative 14. And then you have I times I, which is I squared. And so we FOILed, or we distributed through the parentheses, and now we just need to simplify what's left over. It might be nice if we just took a step right now. Well, let's see here. I don't know the best way to show it. The negative 21i plus 18i is, those are like terms. You can add them together and get negative 3i. So we might as well go ahead and do that. And then the minus 14 times I squared at the end. Remember that I squared is the same as negative 1. And so that's the thing that students sometimes forget about when they work this problem. So negative 14 times negative 1 makes a positive 14. We'll have 27 minus 3i plus 14, and then we can go ahead and write 27 plus 14 as those are like terms here, and so we would have 41 minus 3i for our final answer. Okay, let's do a couple more here with multiplication, and then we'll get to the division. Let's do 3 plus 2i squared. The common mistake here is just to square the 3 and square the 2i. And of course, that's not correct. And you'll recognize it's not correct if you take time to apply the definition of a square. It's that thing multiplied by itself. And so then when you look at it like this, then you see that you need to FOIL, or you need to distribute through the parentheses. And so 3 does get squared to make 9, and 2i does get squared to make 4i squared. But there are two middle terms also. There's 3 times 2i to make 6i, and there's 2i times 3 to make another 6i. And so now we have all the terms that we need. And then I wrote out some extra steps in the previous example. What I'd like to do here is just shorten up the process a little bit. And so the plus 4i squared there at the end, what does that simplify to? If I squared is negative 1, then plus 4 times negative 1 gives you a minus 4. And so then you have 9 minus 4, which is 5. And you have 6i plus 6i, which is 12i. Okay, let's stop right there. And in the next video, we'll do the division.